Okay, good morning, everybody. The title of my talk is quite tricky, ubiquity of hypothesis test cycle, but what I'm going to say is basically this, that is hypothesis test cycles are equal to data circulation, which, well, addresses meaning and value or realizes meaning and value, so it's very important. Let me start with this thing, which is technological singularity. And people are saying that it comes quite soon. And technological singularity is a hypothesis event in which artifacts will become more intelligent than we humans, so that they can generate more intelligent artifacts as well, in such a way that technological developments will become much faster and unpredictable. So the mode of technological advancement is quite different from the past or the current situation. So that's technological singularity. And the major advocates of this thing is Raymond Kurzweil, who asserts that technology is advanced exponentially following Moore's law, which means the semiconductor circuit density doubles in 1.5 years. So his prediction is that this singularity comes in 30 years. And also this prediction is well supported by recent advances in artificial intelligence, in particular such as IBM Watson, deep learning, and other machine learning technologies. And this is deep learning, and I'm going to detail this so much, but this is a 3-layer neural network, and deep learning means that the number of these layers is much more. So for instance, this has how many layers? Nearly 20 or more than 20 layers, so much more layers than this. And deep neural network is a network with so many layers that means deeper than before. And increasing the depth or the number of layers should improve the expressing power and the suppress overlearning better than increasing the number of neurons in each layer, which is theoretically predictable, but it has long been impossible to carry out proper learning based upon these networks. But around 2006, researchers have discovered proper methods to do that. So nowadays, many people are doing these things. So this is part of the reason why many people believe in technological singularity coming soon. But actually, seen from researchers doing real research in artificial intelligence field and the natural language processing field, it seems that technological singularity is very far. So if you look at Google Translate, which is available on a daily basis, if you enter this passage into Google Translate and try to make it translated, then this is what you get. And there are so many errors, so many mistakes, like wrong semantic roles and wrong treatment of unknown word and so on and so forth. And looking at these, so these are very difficult, hard problems, and it seems almost impossible for us to solve these problems in 30 years. So technological singularity seems very far. So why is this? So, and one thing is that those difficult problems are associated with autonomous adaptive systems like life, cognition, society, intelligence, and so on. And these systems operate on the basis of evolutionary method, which is termed by Karl Popper, which is equal to data circulation or hypothesis test cycle. So this is hypothesis test cycle. You set up some hypothesis and test the hypothesis based upon some data, possibly shareable data. and you operate, you run this cycle forever, and that's hypothesis test cycle. And many living creatures or cognitive system or society, they are operating on the basis of these kind of cycles. And it is the working of these cycles that creates difficulty to understand or design such systems. So data circulation creates or realizes value, and which accounts for meaning, which is almost equal to meaning. So meaning comes from value, which is realized by data circulation or hypothesis test cycle. Of course, hypothesis test cycle may not always create value, but only hypothesis test cycles systematically maintain or improve or create values and thus address meanings, right? And cycles or data circulation increase expressive power and complexity of information processing to make systems harder to understand or design is also made hard. And if you remember, if you are a computer science student, you would remember what you learned as part of computational theory, which tells you that it is impossible, in general, not possible to judge whether a computer program terminates if the program contains cycles, right? So cycles are very complicated. So if the information processing systems involve cycles, then it is quite hard or to design and understand those systems. However, if you focus on meaning or value, abstracting away from the cycles, then it might be possible for you to design and understand those complicated systems. So that's what we must do under the rubric of data circulation or science in general. And I'd like to talk about how ubiquitous data circulation is in living creatures or society. So of course, learning and evolution are cycles or data circulation. And you might want to look at more into shorter term cycles, since life is full of shorter time cycles too, such as there are many oscillations in living bodies, like frequencies of 2 seconds or much faster cycles may be there, and so on and so forth. And if there are some synaptic connections in your brain from this to that part, then it is often the case that there are inverse synaptic connections as well. So if you have synaptic connection in one part to another part in your brain, then there may be quite often inverse synaptic connection from this part back to the first part. Also, what is called homeostasis is a typical example of hypothesis test cycle or data circulation around us. And behavior control or action control is also a data circulation or hypothesis test cycle. So there are so many shorter term cycles in daily living as well. But if you look at more interesting examples, that would be more enlightening, I guess. If you look at this result of researches by Takeda-san more than 20 years ago, nearly 30 years ago, who studied the focal length control. This is a picture painted by Andrew Wyeth. This is shown in MoMA, Museum of Modern Art in New York, and its real size is like this. this way. So Takeda-san and experimenters asked subjects, cooperators, to look at this point in a picture, and then this point as well, and back to this point, and so on and so forth. And while doing so, the experimenters measured the focal length, the length of your eyes and to the focal point. And this is the result. There are two subjects. If you look at the first subject, then please focus on this A, which is accommodation, which is reverse of focal length. So if A is small, then focal length is long, and if A is large, then focal length is short. And this F and N represents the far point and near point. So that when the subject looks at the far point, then his focal length is long, and if he looks at the near point, then the focal length is short. And same tendency is clear in the second subject. So if he looks at the near point, then focal length is short, and if he looks at the far point, then the focal length is long. Right? It's rather strange because the distance between your eyes and this point, and distance between your eyes and this point are almost the same, because the picture is flat. However, what's happening actually is if you are looking at the point which is, according to the semantics of the picture, far, then your focal point is long. And if you look at, well, near looking part of the picture, then your focal point is short. So what's happening is this. Focal length control, and the semantic interpretation of the picture are interacting in a circle. So that's one example. The second example is the modal theory of speech perception, which has been discussed for more than decades. And it means speaking entails simulated hearing, and hearing entails simulated speaking as well. So as a speaker, if you are speaking, then of course you are uttering something, and that is fed back to your auditory system, and you try to understand what you have said, and you check what you have said, exactly what you wanted to say. Okay, so that's speaking entailing simulated hearing. And also, if you are hearing others' speech, then you are doing simulated speaking. So if you hear something, then that goes to nervous system, auditory system, and which drives simulated utterance, and check if the simulated utterance is the same as the interpretation of the speech. So speaking accompanies hearing, and hearing accompanies speaking. So they are inseparable in a circle. That's motor control, motor theory of speech recognition. This is robot. The architecture was invented also 30 years ago, and this thing, the cleaner robot, Roomba, is a descendant of such, insect robot invented 30 years ago. And the architecture of these robots looks like this. What's happening here is the robot has one sensor which feeds sensor data to many internal modules, and these modules work at the same time. But the control over actuator is going to be taken by the modules which operated the fastest. So in this case, mapping module returns the answer fastest, more faster than the other modules, then control the actuator. And this cycle running through the environment and inside the robot is up to this mapping module. And of course, in the other situations, other modules like planning, monitoring, exploration may work. So the entire behavior of this kind of robot is a combination of parallelly running hypothesis test cycle. So if you look at this in a different angle, then the robot is following several constraints at the same time. And each constraint module, like inference, planning, object identification, wandering, or there are two wanderings, avoidance, and so on and so forth. Each of these entails hypothesis test cycle encompassing inside and outside the robot, and they are running at the same time. So that's robot. And this is a case of natural language processing. And this is a very traditional architecture for natural language processing, where you input data in terms of text or speech or something like that. And first thing you do is syntactic analysis, then you pass control to semantic analysis, then pragmatic analysis, and the general inference, discourse planning, sentence generation, and finally output is obtained. However, there are many shortcomings of this kind of architecture, such as it's very difficult to incorporate many contextual pieces of information into this kind of computation. So much more appropriate seem from a hypothesis that the cognitive systems can be designed in terms of cycles, where cycles are reinterpreted as values or meanings. This architecture, constraint-based architecture, is more appropriate to design and understand our linguistic competence. So there are several constraint modules like extra-linguistic knowledge, semantic constraint, syntactic constraint, and so on. And they are interacting with each other and turning cycles each. And what's important here is it's impossible to separate comprehension and composition from each other. They are inseparable, and they form a cycle, which is a unit of your cognition, your cognitive system. But if you consider this case, which is Broca's aphasia. Broca's aphasia is a very strange phenomenon. So patients can comprehend sentences, but they cannot compose sentences. So if you tell them, like, would you open the window, then they would open the window. And if you tell them, close the door, then they would probably close the door. So they generally understand what you say. They generally understand sentences. However, it's almost totally impossible for them to compose sentences. So if you show this series of pictures to the patients of Broca's aphasia and ask them to describe what's happening here, then what they can do is to say something like this, which is almost nothing. So they cannot compose sentences almost at all. Right? If this interpretation of Broca's aphasia, that the patients can comprehend but cannot compose sentences, then that may refute our hypothesis that comprehension and composition are inseparable, right? Because it seems that in this aphasia, only composition ability is missing, whereas comprehension ability is preserved, right? However, if you investigate these patients, then you would discover something more intricate. That is, Broca's aphasia is due to the failure to access grammatical knowledge rather than failure to compose sentences. Well, if you cannot access grammatical knowledge, then it is impossible for you to compose sentences. So that accounts for failure to access grammatical knowledge accounts for failure to compose sentences. However, that is also consistent with the fact that they can understand simple sentences, although they cannot understand complicated sentences like this. The car is pushed by the truck. The girl whom the boy is pushing is tall. So if you show or make them listen to these sentences and ask them to choose between, say, two pictures. In the case of the first sentence, you would show the patients two pictures, where one picture shows the situation where a car is pushing the truck, and in the other picture, the truck is pushing the car, and you ask him to choose between the two, the right one between the two, from the two. And they answer correctly only 50%, which means that they don't understand these sentences. The 50% is the same for the second kind of sentences as well. So Broca's aphasia patients do not have access to grammatical knowledge. They can understand simple sentences like open the door, because they have access to lexicon, dictionary, and of course they have access to extralinguistic situations. If you ask them to close the door, if you say them, please close the door, then he would understand the word such as close and door, and he will understand that you kind of look at this, you want me to do something, and comprehending all these pieces of information, they will be able to open the door or close the window and so on and so forth. However, they cannot understand these little complicated sentences because that task requires access to grammar. Okay, so as a result, our hypothesis that comprehension and composition are inseparable is not refuted by these phenomena associated with Broca's aphasia. Right, so our cognition, intelligence is full of, or life is full of cycles or data circulation. But going back to technological singularity, we must have better data circulation technology. Although machines outperform humans in recent years, so for instance, AlphaGo defeated the human champion of Go by using deep learning plus reinforcement learning. But okay, that means machines are better than humans in complete information, zero-sum games. However, most important problems like automatic driving, conversation, and so on and so forth, are not complete information. They are partial information. And they are not zero-sum, but they are collaborative situations. So in automatic driving, the drivers, robot drivers must be collaborating with each other in order not to collide with each other, for instance. And also in the case of conversation or dialogue, the dialogue participants must be collaborating with each other in order to share the meaning between them. And those tasks require some very delicate or very high kind of meta-knowledge for data circulation that are foundation for linguistic competence, collaboration, and so on. So one is symmetry bias. So if you look at the case of language, if you know an apple, some fruit is called apple, then you know this word apple means that fruit. Well, do you understand that? This would illustrate that better. So non-human animals lack this bias, symmetry bias. And animals other than humans cannot use language. The reason is that they don't have this bias. So if human experimenter teaches, for instance, a chimpanzee to use language by, let them learn by showing these fruits and in such a way that they can take up appropriate cards with corresponding words on it. So if the experimenter shows the chimpanzee a banana or a bunch of bananas, then the chimpanzee expected to pick up this card written banana. And if he shows an apple to the chimpanzee, then the chimpanzee is supposed to take up a card written apple. And it's possible for us to teach this task to chimpanzees and bonobos and those, kind of not monkeys, but apes. So they can learn this association from objects to words. However, even when they have learned this ability to associate from objects to words, it doesn't mean that they have learned the inverse association. So if he learned this skill, he cannot do this reverse task. So if the human experimenter shows the chimpanzee this card written banana, the chimpanzee cannot rightly choose between banana and apple, right? So this task must be, the chimpanzee must be trained in terms of this task, even after acquired this ability. But in the case of humans, if you learned that this thing is called banana and this thing is called apple, then you would be able to pick up banana by looking at this, and you will be able to pick up an apple by looking at this. However, that doesn't happen in the case of chimpanzees or other apes either. And actually, only humans have been, observed to display this symmetry bias so far. And that's one thing, that's most basic kind of meta-knowledge or data circulation, or delicate or complicated data circulation. And another thing is collaboration bias. Collaboration bias is my coinage, which is an inclination for shared value, an inclination to collaborate with each other. In particular, this is quite important for us to use languages, because the speaker and the hearer must collaborate with each other in order to share the meaning that is speaker's intention, even if they are enemies, right? So if you can talk with your enemies and understand what they say. And if your enemy says something to you, then you will try to understand his or her intention. So his intention or her intention is the meaning of his or her utterance. So that's that's how language works. So in that sense, even enemies would collaborate in order to use language. So that would be based upon probably on this collaboration bias, deeply installed in intelligence or cognitive system. And the problem is, technical problem is that such meta-knowledge is quite hard to learn automatically. And they are actually absent in deep neural networks or other machine learning technologies. If you look at the architecture of deep neural network, there's no part of it which may support these kinds of meta-knowledge at all. So learning individual cases, learning these biases for individual cases may be possible, but it would seem very, very difficult for machines to learn these biases for general cases, not in particular cases. However, we don't have to make machines to learn these biases in order to create intelligent machines. We would be able to manually encode those biases into the architecture of your robots, for instance, and that may make some breakthrough to bring us to technological singularity in 30 years, maybe. So that's one thing, that is we need some more delicate or sophisticated technology to do data circulation. And another thing is we need more data too. If you look at the current situation of research and development of artificial intelligence, data preparation, that is data acquisition, normalization, annotation, etc., consumes more than 90% cost for the development or research in artificial intelligence. And if you look at another aspect of the society, documents are read much more often by machines than by us. If you consider your papers, technical papers, the number of readers per paper is steadily decreasing. There are much more papers written per year. And the ratio of the number of papers and the number of researchers is increasing because Chinese and those people are also writing papers these days. That's one thing. And in a big project in Japan, they are trying to use IBM Watson to read through or extract knowledge from papers in PubMed. PubMed is a repository of medical science papers. And last year, 2015, PubMed registered about 3.6 million papers per year. And a research project would be able to hire up to 10 people, and you might want to make those 10 people to read through PubMed papers, but that's totally impossible. So what they are trying to do is to use Watson to read through those papers and to extract some useful knowledge. Okay, so more and more machines are reading the documents rather than people, right? So do we have to write papers for the sake of humans? Maybe no. We should be preparing documents for machines to read them, right? So improvement to productivity in that respect, or in the creation and circulation of machine understandable data, documents, is the most important task for the development of AI. And that should be quite clear. So how do we do that? For instance, if you look at this kind of traditional form of document, which is, by the way, pathology report, and you don't have to understand the detail of this Japanese passage. And you would often notice that this kind of traditional format document is, well, not just hard for machines to understand, but also hard for us to understand as well. Even professional pathologists don't understand some part of this kind of document written by other pathologists. So what to do in order to escape that kind of problem? So this is one solution, one possible solution. You will be able to introduce this kind of structure, semantic structure into the document in such a way that the document would be more understandable to machines and also more understandable to humans, people as well. Right? So to do right now, from now on, would be something like this. So big data understandable to both humans and machines should be created mainly in daily living and work, rather than temporary R&D projects. So this creation must be on a sustainable basis. That will be part of continuing daily living and work, rather than physical temporary R&D projects. For the sake of both automatizing business, your living and work, and also providing big data to research and development. The problem is that only humans can create such structured data. And most important thing would be education and employment creation for those people to create such structured data. Well, I think that's all. So thank you for your attention. Questions and comments are welcome now. I will give these slides afterwards. Sorry, not beforehand. Any questions, discussions? Okay.
Thank you for your presentation. I want to know that whether you think it is possible for a machine to really understand because I think sometimes the paper I think is also hard to read even for the research.
Yeah.
Whether it's possible one day.
Well, that's due to the definition of understanding. But what they want is not totally not to make IBM Watson totally understand what's written there, but extract some causal knowledge, like if you dose this medicine to this kind of patients, then that would cause this and this phenomena after that, and so on and so forth. So that kind of factual or objective state of affairs will be possible for machines to extract from the text. And what's important, what's necessary for these kind of research is that sort of thing, rather than deeply understanding the very artistic or delicate aspect of the text, but just the factual stuff. Other questions?
I have a question about his question. So actually there can be some incorrect papers, but how to recognize them?
You don't. Well, this reading comprehension doesn't mean that machines should recognize those failures or lies in the papers, but they should just extract what's written there logically rather than interpreting those pieces of information. And that would be a great help for humans to use what's written in there, rather than for humans to read those papers all the way through. Did I answer your question? Okay, more questions, comments?